Yeah, okay. So this is a series of 3 lectures. Today, probably tomorrow, we have to sort that out, and then in 2 weeks' time. I'm going to be talking in this first lecture. I'm really starting at the beginning, but I'm going to try to go through the beginning relatively quickly. So I'm kind of assuming that, at least for folks who haven't really thought very much about Bayesian statistics, that you'll be able to join in. If I'm going, I assume that's kind of the right level. If that's wrong, though, I can speed up. So let me know. So let me, oops.
Oh, and also turn on your video because they may not see.
So
is this Zoom meeting getting recorded?
yes. I can also share my slides. That occurred to me. We would have to figure out who's,
Send
email addresses and things like that.
No, send it to me. I'll put it on our webpage. There is a webpage for that.
Oh yeah, that's a good idea. We can just share it on the page. Okay.
It's not. Okay. Never mind. It's okay. You don't worry about it.
Okay. So why can't I control this?
Oh, it is working. Never mind.
Yeah, you're worried about different things than I am. Oh, there it goes. Okay, it's very strange. Okay, everything's a little weird today. Okay, so where to start? I'm going to be talking about Bayesian statistical methods, and I want to place that a little bit in the context of how people think about data analysis in 2025. So I say up there's a massive new data streams are opening up a world of opportunities for data scientists. Generally speaking, that's certainly true of people working on data in astronomy. Improved data quality and quantity is leading to more interesting statistical models. So it's much easier to kind of hardwire your science into a statistical model and to build statistical models that are specifically tuned to the complexities of your data, thinking about the data collection, the telescopes, the calibration, observational effects, and the science, the physics, the physical models that are inside of there. You can think of that in the context of maybe statistical models, and you can also think of it in the context of more learning-based, machine learning or statistical learning. And kind of in that dimension, I write there data-driven versus science-driven models, where in the extremes, and this is a caricature, but on the extremes, these data-driven learning models are really meant to be kind of completely ambivalent to the kind of data and the kind of statistical or scientific questions you're answering or asking and trying to answer. So you have a machine, a black box that you put data into, and out comes science. And there's ways that's a bit of a caricature in some ways quite silly, but you could actually do that in some cases nowadays. At the other extreme are these science-driven models where everything is built upon the particular science question that you're trying to ask. You build the machinery around the scientific question. In reality, usually we do something somewhere in the middle. We're not maybe interested in modeling the calibration of our instruments, fully. We want to account for calibration properly, but we're not interested in the details of the calibration. We're not trying to do statistical inference for the calibration. So we might use different levels or different kinds of modeling for different aspects of the model. Predictive models versus descriptive models. Again, predictive models means I want to predict, what's going to happen next. If I'm Google and I'm going to put an ad in front of you, I don't care why you click on the ad. I just care if you're going to click on the ad. Whereas in a science setting, the why is the whole point, right? So some methods are more attuned to the, asking the why questions and not asking, just trying to do prediction. Trade-offs, computational speed versus statistical principles. Learning methods, as we all know, are massively faster than carefully designed statistical models, and sometimes that's a deal breaker, and sometimes it's not. It depends on your data, your questions, and your goal. Statistical models, I say principles, quantifying uncertainty, and those sorts of things are a little more hardwired in to statistical models than learning-based models. So, that's the big picture. What we're going to be talking about in these lectures are the Bayesian science-driven descriptive models by and large. I'll go through this very quickly because these slides I've used for other purposes, and I start by talking to people on how much data there is in astronomy and how the data is can be very specific to the scientific question. You need to account for differences in the way the data is collected, Poisson data versus Gaussian data, all of those sorts of things. But since you're astronomers and we started a little late, let me skip over that. And say, okay, even if you're thinking about these more science-based statistical models, there's another bifurcation, which is Bayesian methods versus what we call frequentist or likelihood-based or more traditional methods. And this is an old plot at this point, but I did kind of a lot of work to make the new plot, and it shows the same pattern that astronomers thinking about statistics, first of all, has grown enormously and continues to grow. And within statistics, thinking about Bayesian methods is growing equally fast. What are the advantages and disadvantages of thinking about a problem from a Bayesian point of view? Directly model complexities of sources and instruments. Again, from a Bayesian model, we can, like I was saying before, we can hardwire our functional descriptions of the science and the instruments into our models. Skip the next one. Combining multiple sources of information, we'll come back to that, but Bayesian methods in particular are very good at taking different kinds of information that all lead to the same scientific question and combining them in a principled way. Allow hierarchical or multi-level structures. So you could think about modeling individual objects or sources, such as stars. Like what are the physics in the star? What is used based on the data from observations of this particular object? But I might also, or at the same time, also want to be learning about the population. So making a luminosity function accounting for selection effects. And there's going to be statistical questions at both levels, but maybe the Poisson nature of the data coming from a particular source, and then the population effects, putting that all together in a coherent analysis. Sophisticated computational methods are available for fitting these complicated models. That's going to be the topic for our second set of lectures. The big challenge, why isn't everyone Bayesian, is prior distributions. And we'll formalize this later, but just have that in the back of your mind. Prior distributions require me to say something about what I believe or expect the range or values of unknowns to be in advance of doing my analysis. And for many scientists and statisticians, that's a non-starter. If I have to, I don't want to do that. It sounds subjective, right? I want the data to tell me. I don't want anything that I think in advance to affect my statistical analysis. Of course, that's impossible too, because there's all kinds of things that you have to do in any statistical analysis and choices and decisions you have to make. But this adds another very, very seemingly subjective one to the list. Okay, so outline of topics. Today, we're going to try to get through the first two, or at least most of the first two, background and basic models. So kind of the basics of thinking about things from a Bayesian point of view. Model fitting, so Markov chain, Monte Carlo sorts of things in the second lecture. And the lecture in 2 weeks will be developing more complicated, sophisticated modeling. I won't, you'll get these slides so you can look at those in more detail, that list. I won't repeat myself too much. Okay, so the very first question, and it's quite fundamental actually to thinking about things from a Bayesian point, is what do we mean by probability? So I have a few things listed here. I could ask the probability, if I roll 2 dice, the probability that they both came up with the same number of dots. I get snake eyes or a pair of 2s or a pair of 3s. Or I could ask, what's the probability that, maybe I should say, it's going to snow tomorrow? And those are kind of very different questions. And statisticians and probabilists argue quite a bit about what those, how to answer those kinds of questions. So I won't ask you, I'll just, tell you. There's what's called a frequentist definition of probability. And that means I have an experiment, and it can be a very simple experiment, like rolling a pair of dice. And the probability is the long-term proportion of time that a particular outcome happens. So if I roll my dice over and over and again ad infinitum, the frequency definition would just say that the probability of getting, say, snake eyes, 2 1s, is the long-term proportion of times that I get 2 1s as I roll the dice again and again and again and again. Nice, well-defined, seems mathematical. But you can't answer, what's the problem with that definition? You can't answer questions that you probably really want to. What's the probability that it's going to snow tomorrow? Well, you can't repeat tomorrow. There's only one tomorrow. It's going to snow or it's not. But still, if I say the probability it's going to snow tomorrow is 90%, or if I say the probability it's going to snow tomorrow is 5%, I've conveyed information that has meaning, right? You understand something about one, maybe not in a really exactly precise way, but there's a distinction that I'm making that's meaningful. And it seems a little silly to say, I need a different word. You can't use probability because you can't repeat tomorrow. Right? So mathematically, what is a probability? This is those two dice. I rolled them twice. There's 36 possible outcomes. And there's what we call the sample space is the set of all possible outcomes. So you can see nicely enumerated these 36 or depicted these 36 possible outcomes. Mathematically, a probability is a function that takes values on the sample space. So that means it has to assign for each of those 36 possible outcomes, it has to assign a number. And a probability has some properties, probability functions. They have to be non-negative. It's nonsense to say the probability of something is negative. The probability of the whole sample space, if I roll the two dice, the probability of the whole sample space of the whole thing is 1. And then the only other rule is that if I have two disjoint sets, the probability that one or the other happen is the sum of the probabilities. So if I want to say what's the probability that I get 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, 2 6s, with ors in between, I should sum up those individual probabilities to get the total. And that's it. That's what a probability is. Notice that the mathematical definition doesn't tell you anything about these questions, right? What does it mean? It's just a function. It's nothing more than a function of mathematical construct. What it means in the real world is the mathematics is completely agnostic about. It's up to us to decide how we want to use this mathematical tool. And some people are going to use it with a more restrictive definition. A probability only makes sense if it's something that can repeat again and again. And some people are going to say, well, I'm going to use a probability much more generally. I'm going to say the probability is a tool that I use to quantify, maybe roughly, my knowledge, beliefs, summarize my information. The probability it's going to snow tomorrow is 90%, based on, looking at meteorological data and comparing the day with past days and other things like that. So what this is important is because it's a Bayesian statistician needs to have this broader idea of what a probability is than a frequentist statistician. Doesn't mean that a Bayesian won't also want to use this more frequency definition when possible. If I'm in the business of computing the masses of stars, and I give you what I call a 95% interval for the mass of a star, and I give you lots and lots of these because there's lots and lots of stars. Well, hopefully about 95% of them will contain the true value, the true mass of that star. That's a real question that you can really quantify. And if I'm a Bayesian or not, I'd still like that to be, that when I say 95%, that not to just be about my beliefs, but I'd like my beliefs to correspond to my ability to actually give you confidence intervals that contain true values. When that's a reasonable thing to quantify. But when there's not a repeatable thing like that, I still want to be able to use probability. Okay, so the calculus of probability is based on these things called density functions, or PDFs, probability density functions. And this is just a simplification of a way to keep track of probabilities, right? Because the probability function, I have to enumerate all possible events. But if I start talking about the masses of stars, what are all, it's like uncountably many masses. So I don't want to keep track of that function. The way I do it is by having these, density functions, and I tabulate probabilities as integrals under the curve. It's just a way to tabulate the function. So this is a normal curve, and I want the probability that my variable is between this value and this value. It's the area under the curve. one dimension. Same thing in 2 or 3 or 4 dimensions. It's just instead of, I can't make the pictures anymore. We call those things joint probability functions. And we have to say the probability that, x is between a and b and y is greater than c is the integral, the corresponding integral over that region. That's completely fine. And then we have something called a conditional probability. When we have more than one variable, we can say, given that the one variable takes a particular value, what's the probability that another variable takes a value? And the way we get at that is by computing ratios of probabilities. Okay, so that's basic probability calculus. And it leads to what's called Bayes' theorem, which is, and you might guess is fundamental to Bayesian statistics. So Bayes' theorem, now, why this is fun, Bayes' theorem you can use for anything you want. Bayes' theorem is how you switch probabilities. So if, you go to a doctor and he says you got a positive test for something bad, say cancer, you might say, well, how reliable is the test? And he or she tells you that 90% of people actually have cancer, have a positive test. And you're like, well, that doesn't actually help me. I want to know, given that I have a positive test, what's the probability that I have cancer? I want to flip the area of the direction of the probabilities. And Bayes' theorem allows you to do that, right? So basically, you have the probability of y given x, and it's written in terms of the probability of x given y, and you have these other marginal things you have to pretend yourself with as well. For statisticians or Bayesian statisticians, this is important because we're going to think about, in this case, x is our data, and y are things that I want to know about, like the mass of a star. So I'm going to say if the mass of the star is, y, the distribution of data, well, I know my data is noisy. Maybe it has Gaussian errors. Maybe it has Poisson errors. So I can write down the distribution, like something about how my telescope works, right? But I want to go from that to the other thing, which says now that I have my data, the x, what's the probability of that the mass of the star takes particular values, okay? So Bayes' theorem is central to that. The bottom of the slide is just deriving Bayes' theorem. You don't really, you can look at that later. It's easy enough. We just use the definition of conditional probability twice. This is a little more important here. The probability of y given x has these marginal probabilities and the conditional in the opposite direction. And what I did here is I got rid of the proportional. I made it proportional and got rid of the denominator. And the reason is because this is a probability function. The second property of a probability function is that if I integrate it over the sample space over all possible values, it has to integrate to 1. So I know that this thing must integrate to 1 as a function of y, because it's a probability of y. This doesn't involve y. So I can find, if I integrate this thing, it's equal to that. So I can kind of not worry about that. And why is that that turns out to be helpful? Because this thing, usually I'm going to be able to compute these two things relatively easily. And this one I get by integrating that. And if I don't have to, integrals can be tricky. If you have lots of dimensions and it's easier if you don't have to deal with those integrals. So often we'll write Bayes' theorem with a proportional, ignoring the denominator because we're treating this as a function of y, and so that it gives me all the information I need. And we'll kind of see how that works in a moment. Okay, so this has all been a bit abstract. So let's go to a kind of an example that's a little more concrete. A simple Poisson model. So suppose you have a single bin detector. What could be simpler than that? I'm going to have a single count, a single number. It could be more than one. Single count kind of sounds like it's only one. But I'm going to say that follows a Poisson distribution. This is going to be something about how bright my source is. So like per unit second, per unit area, per unit second, something like that. This is what I'm interested in. And tau is just how the exposure time. If I look at the thing twice as long, I expect to get twice as many photons, right? And I want to learn about, we'll say tau is known. I just know that. I saw how long, I recorded how long I used the instrument. And what I want to do is learn about lambda s from y. Well, this thing is the distribution of the data given the parameter
And as a Bayesian, I want the distribution of the parameter given the data, right? So I'm going to flip the conditioning, that's Bayes' theorem. Okay, step by step though. First, this is the distribution of, this is the Poisson distribution. It's called the probably mass function because I don't integrate it because there's 0, 1, 2, 3. I only, there's not a continuum of values, so I don't have an integral, I just sum. But that's essentially the same thing. You can see the expected count is here, the exposure time is there as well. We call that thing the sampling distribution often in statistics, but that's maybe not important. The likelihood function, one way to kind of learn about the parameter, the likelihood function is the sampling distribution viewed as a function of parameter. Constant factors may be omitted, so I can, as a function of the parameter, I can get rid of this thing. There's nothing here. I can't get rid of anything else because I want to keep the functional form of lambda. Okay, and the maximum likelihood estimator is the value of the parameter that maximizes that likelihood function. So let's look at that. I wrote it all down here. So the likelihood function, exactly the same function I had on the previous slide. And now it turns out often we take logarithms just because logarithms make things easier. If you want to, if you want to optimize this thing, it's going to be better behaved. So I've taken the logarithm, I've gotten rid of the y factorial because it's just a constant, because eventually I want to maximize this thing as a function of lambda. And I've plotted the likelihood function. The likelihood function is the solid curve. And the dash curve is a Gaussian approximation. So that's a Gaussian with the same mode. Although I plotted it, it's a little off there, but it's the same mode and the same curvature. So at the mode, the curvature, how quickly it falls off is the same. And often the way, if you're doing maximum likelihood estimation, you'll compute this curve. You will find the maximum value. That's going to be the most likely value of the parameter. And you can assess the uncertainty by looking at how quickly the curve falls. If the likelihood function falls off very quickly, if it fell down like this, that would mean you have more information about the parameter. Okay. Why I plot them both, though, is because you can see you see essentially if you're just looking at the mode and how quickly it falls off, you're looking at the Gaussian approximation. But the Gaussian approximation isn't awfully bad here, but it's also not quite right. Because you can see, I've cut it off at 0, but it continues to negative values, and it's an expected count, so it's not going to be negative. And it's kind of underestimating the probabilities or the likelihoods of large values as well. So maybe we don't want to use the Gaussian approximation. Maybe we should stick with the likelihood function itself. Let me just skip that. So what's a Bayesian going to do? Remember, I have the, maybe I should flip back. Where's my Bayes theorem? Oh, here. So we're talking about, this is my Poisson distribution, probably the data given the parameter. And I have this other thing here, which is y is the parameter. This is my probability of the parameter not given anything else. So we call that thing in Bayesian analysis the prior distribution. The marginal distribution, the distribution of the parameter before conditioning on the data. It quantifies knowledge regarding parameters obtained prior to the current observation. Now, it could be real knowledge, but I mean, quantifiable knowledge. It could be you did an experiment yesterday, or you have an observation from 2 years ago about this particular source, and you did a statistical analysis that told you something about the mass of this source, or the intensity, or whatever it is. So you have information that you're going to put into your analysis from previous analyses. Or it could be of a completely new source, a completely new kind of source, something you know nothing about. And you still want to have to, say what you think about the likely values of the parameter. So in my Poisson model, we're going to use what's called the gamma distribution. The gamma distribution is a flexible family of prior distributions. I've just shown you, plotted a couple of examples. A flat one that looks a lot like, but it's not exactly a uniform distribution, and a very skewed one. So the gamma distribution is quite flexible. So whatever my information is, I can probably find a way to put it into a gamma distribution. I've given you the functional form there. You can write down the mean or the expectation of that distribution, the variance of that distribution. And I can apply Bayes' theorem. Bayes' theorem says, now writing it in terms of the parameters, I want to know the distribution of the parameter given the data, and that's going to be the likelihood times the prior times this mysterious other thing, which is the marginal distribution of the data. But luckily, I can get rid of that because that's the denominator. It doesn't have anything to do with lambda. We don't need it to compute this thing. So I can just write it as proportional to the likelihood times the prior. I write down the likelihood and the prior from the previous form page, and I kind of move them around. And what you can see is that the functional form, this thing is lambda to a power e to the minus lambda times something. Lambda to a power e to the minus lambda times something is the same. So that means that this thing is also a gamma distribution, but it has different parameters. And that makes my analysis very, very easy. That's why I choose the gamma distribution in this case, because it looks like a Poisson distribution. So we'll come back to that nice property in a moment. But this is also, this here is looking at three different, in my analysis, I guess I didn't mention that. I have a made up data set. It's just a little data set. Where did I say it? Yeah, three. I have, I looked at the thing for, say, 1 second, and I saw 3 counts. So it's a little data set. With that small data set, you can see 3 prior distributions and the corresponding 3 posterior distributions. This is what we call sensitivity analysis. Especially with small data sets, your choice of prior will make a difference. So your posterior distribution that you get depends and changes depending on your prior distribution. And so that's maybe okay if, for example, I have a good reason for picking a particular prior distribution. It's based on a previous analysis. Why not? If it's just something I pick because I need to pick something, then I certainly want to be aware of this and think about how, how my science is changing based on something I just picked. That seems kind of bad, right? If I just picked it. The good news is we'll find that I only have 3 counts here. As I get more and more counts, I'll find that those things all come together. But with small data sets, you definitely want to worry about this sort of stuff. This gamma prior is called a conjugate prior. And I've just written down the general formula. I started with Poisson data. I have a gamma prior on the intensity. The posterior is also gamma. Conjugate means that the prior and the posterior are of the same family or have the same form. And it's because the likelihood and the prior kind of match. A Bayesian estimate, once I have the posterior distribution, the expected value, the mean of that posterior distribution is a good estimate. And I can estimate the standard error using the standard deviation of that distribution. I have a distribution. Its mean tells me, the most likely value in some sense, and the width of the distribution tells me the level of uncertainty I have. And so the standard deviation is a good way to measure that. What's also kind of nice is I can look at this a little bit and start to think about what the alpha and the beta actually mean. If all things being equal, if I wasn't being a Bayesian, and I saw 3 counts, and I looked at, after watching for 1 second, I would say my best guess is 3 counts per second, 3 over 1, ignoring the alpha and the beta, right? But so what the alpha and the beta are doing is saying, you can think about the alpha and the beta, or that gamma prior distribution is giving you as much information as an additional observation of time length beta, where you saw alpha observations. And what's nice about that is it lets you quantify precisely how much information you're bringing to the data. And it also, if you're basing it on a previous experiment, gives you a way to turn it into something meaningful. How long was that previous experiment? How many counts did you see? Maybe
I just want to downweight the previous data. So even though I watch for 100 seconds, I'm only going to count it for 20 seconds or 5 seconds or something like that. Or maybe
Tau is 1,000 seconds, and I really don't know what alpha and beta are, but I'm going to make beta 0.1. And I say, well, my data is counting for 1,000 and my prior is counting for 0.1. I'm putting 10,000 times more weight on my prior. Well, probably when you do something like that, you'll find that the sensitivity analysis, the prior doesn't matter very much. Okay. But it gives you a way to kind of quantify what you're bringing to the data. We call that sometimes prior data. And this slide is just saying all the things I just said.
Can I ask a quick question?
Yep.
So choosing alpha and beta to be 0 is effectively saying 0 counts in 0 seconds. So is that that will give you a uniform prior, right? Is that in some sense something that we can consider the natural prior?
You can definitely do it, and we'll come to it. It's called an improper prior, I think. I have to go back and look at the functional form. You said it was flat. So if it's not flat, if alpha is 0, it's going to be 1 over lambda.
Oh,
This will go away. Yeah.
Yeah.
Yeah. So, yeah. So we'll come back to later in the lecture. Hopefully, we'll talk about improper priors and things that you can do like that. But it's it's definitely something to consider. You have to be a little careful when you step outside of reality. That is to say, if your prior distribution isn't actually a distribution, you have to be a bit more careful. So the thing is that 1 over x is not integrable on the real line. So it's not a distribution.
But is that in some sense a preferred uninformative prior?
I wouldn't say it's necessarily preferred, but it's definitely one you want to think about. That you would run into trouble if you had if y is less than alpha, if y plus alpha is not positive, then your posterior is not proper and you can't do inference. But now we're way into the I have a massively uninformed prior and no data. I'm going to be in trouble. Well, sure, no one's really expecting that to work. But using something like, a prior that it's definitely a prior I would have high on my list of priors, but we'll come back to the kind of ways to evaluate these things. Okay, so where was I?
Sorry, ask a question.
Of course, Doc.
So it seems like it makes sense to use the gamma distribution, and it gives you a lot of mathematical freedom, but is the gamma distribution, does it account for all the possible priors that you want to use?
No, the thing is that, so this is mathematics, right? So where's that little box I had? Here. The gamma prior, it's mathematically convenient because of this, but you can take the likelihood and multiply by any prior you want. You might, if you have a prior somehow that looks like this, gamma is not going to do that for you. If you have 2 possible things, and that's completely fine. It just means you need to do things more numerically than mathematically. Usually people don't, they usually want priors like the one Vinny was saying, not ones that have a lot of detail. So for most cases, you'll find a gamma prior when you use Poisson data that's exactly what you want. But there's no reason except it makes things easier that you have to stick with gamma priors. Okay, so we are really, we started at 10:30. Yeah, we have about 50 minutes. Okay. Let me skip. I want to make sure I just kind of focus on the things that are most important. Okay, so Bayesian statistical summaries. The full statistical summary is the posterior distribution. Researchers often, like when you write a paper, you need an estimate and an error bar. And so often we give the estimate and the error bar by the mean and the standard deviation of the posterior distribution, as I was saying earlier. But is this enough? So I want to think about other ways that I might summarize the posterior distribution, or cases where the mean and the variance, or the mean and the standard deviation are not quite the right thing. Okay, so intervals.
if I want to give you an interval estimate, the mass of the star is likely to be between X and Y, or between A and B, or I say L and U, lower and upper.
The general way you do this from a Bayesian point of view is I want to find L and U so that the integral, the area under the curve of the posterior distribution, since it's a 95% interval, is equal to 95%. So like a 2 sigma error or a 1 sigma error. Okay. More generally, maybe it's not an interval. Let's look at cases like that, or maybe I'm working in higher dimensions, so it might not be L to U, but some space that has probability 95%. But that choice is not unique. If I want to say 95% interval, I can start at 0 and put 5% in this tail, or I can put 5% in this tail and go all the way to infinity, right? And maybe both of those are a bit strange. If I want 95%, maybe it makes more sense to put 2.5% in either side, right? So the point is that just this doesn't tell me what the interval is. I need to still decide how to attribute the probability. So a couple of ways that people do this. This is the equal-tailed interval. That's what I just described. I did with 90%. Probably just make the picture a little easier to see. If I want an equal-tailed 90% interval, I put 5% on each side, take the 90% in the middle. That's a really nice choice and a very easy choice. One thing is if I take, this choice of is unaffected by transformation. So if instead of looking at the intensity, I start wanting to take the logarithm of the intensity or the square of the intensity or anything monotone, the intervals are invariant. So that is to say, you get the same interval on the square scale or the original scale. That's nice. And also, it's very easy if you're working with Monte Carlo. We'll talk about often Bayesians work on Monte Carlo. And Monte Carlo means is the way that I do all of these integrals is I get a sample of values from this distribution. And how can I convert those values into intervals and things? So we'll come to that tomorrow. But this is a very easy and most standard. There's something that in some ways is nicer. It's called the highest posterior density or HPD interval. And what the HPD interval tries to be is the shortest interval. If my science is going to be better if I constrain the parameters more. So I both want to say it's 95% and have it as narrow as possible. That's the HPD. And the way you get the HPD is you make sure you use all the area where the curve is the highest. Because if I want 5% probability here, I'm going to, it's the area under the curve. To get 5%, it's going to be narrower here than it is going to be here. So you imagine, add this lambda thing. As I take lambda down, these things spread out, and the area under the curve gets bigger. So I start at the very top where the curve is the highest, and I just keep pushing this dotted line down, and the interval gets wider until I get the probability I want. Harder to compute in higher dimensions, but it's in some ways what you would like. It can be different. This is comparing the HPD on the left with the equal tail probability on the right. I'm sorry, I got that backwards. The equal tail on the left with the HPD on the right. When you have a skewed distribution, they can be different. If you have a nice symmetric distribution, they'll be exactly the same. Here's an HPD interval from a real science problem. This is the location of a spectral line. And you have a Poisson spectrum, X-ray spectrum. You'll have little, you have a nice power law, say, and you'll have different regions along there where there's Poisson variability, where there's a few extra counts here and there, just the ordinary Poisson variability. Anywhere you have a few extra counts in neighboring bins, well, that could be a line, maybe. And so when you do a proper Bayesian analysis, you start to get a posterior distribution that has all these modes. The line may be, the line could be at 5.5 or 2.75 or 2.2, each with their own probability. So so in this case, equal tailed interval would be quite silly, right? If you just say you just lop off these two bits and say this is my interval, right? That would be quite silly. It's probably more sensible to say, well, it could be here, 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 and give a probability for each of those, right? And then that's really what the HPD interval is doing, right? It's taking the areas with the highest probability and just using those. Skip this part too. Nuisance parameters. This is nice because it also tells me, I'll illustrate with Monte Carlo, how Monte Carlo works. Nuisance parameters are quite tricky generally in statistics. A nuisance parameter is exactly what it sounds like. It's something I'm not interested in. I have a source that's contaminated with background. I don't know how strong the background is. I'm not really interested in the background. I just want to make sure I account for the background, right? I don't really want to estimate the expected background per unit area per unit time. But suppose I have data and I can estimate it. And I get a posterior distribution, the source expectation and the background expectation, and I get contours, because now there's two parameters. So this is the posterior distribution. I have two priors, but that's not really the point here. The solid ones compared to correspond to this. This is the posterior distribution of lambda S, which I get by just integrating out lambda B. So there's a very well-defined way to deal with nuisance parameters when I have a joint distribution. I just integrate out what I don't like. Integrating, like I said before, can be a little bit of trouble. But if you have a Monte Carlo sample, so this is again my posterior distribution, I've gotten a sample from it. If I want this, the marginal distribution of lambda S, well, what do? I just ignore lambda B. I make it say this is a histogram of lambda S. Okay, and this curve here is because I've numerically integrated it. I can compare it and just see that you get the right thing. But the integration, once I have a Monte Carlo sample, integration is trivial. I just look at the things I'm interested in. And we'll see other reasons like we like Monte Carlo in the next few slides, I think. Let's kind of stick with the program here. Okay, so let me look at another simple one-dimensional example. This is the binomial distribution. That's this, Poisson distribution for counts, binomial distribution. And this is for hardness ratios. Hardness ratios are looking at you probably know this, but it's the lowest resolution summary of a spectrum. You look at the hard counts, the high energy counts, and the soft counts, the low energy counts, and you're interested in how many, like the relative frequency of the low and the high energy. So you just have maybe some cut point. And I'm going to say capital H is the number of hard counts I observe, and capital S is the number of soft counts I observe. And I'm going to model those both with Poisson distributions. Again, I'm thinking about X-ray data, so that seems sensible. And little n, that's the total number of counts that I observe. And I made it a little n because I'm not going, although it is random, I'm not going to treat it as random because I'm not interested in the overall brightness of the source. Little n, or if I made it a big N and modeled it, it would be good at telling me how bright the source is. But I'm not interested in how bright the source is. I'm interested in the relative brightness of soft and hard. So what I'm going to do instead is I'm going to model this with a binomial distribution. It turns out mathematically, it's a undergraduate probability example to show that if you have two independent Poisson random variables, one of them, given their sum, is binomial. And it kind of makes sense if you think about it. But you can show that it's not a modeling thing, it's just a mathematics thing. So I'm going to say that H, the number of hard counts, given the number of counts, follows a binomial distribution. N trial, it's like flipping a coin n times. And the probability of a success, where a success is getting a hard count, is the relative probability and the relative expected count for hard and soft. Okay. And so that pi, that's the parameter I want to try to learn about. And maybe I expect it to be about 20% because there's usually more soft counts than hard counts, depending on where I draw the line. So how am I going to do a statistical inference for a Bayesian statistical inference? Well, we're going to do the same thing as we did before. We're going to have a likelihood and a prior distribution. This is the binomial likelihood. It was a lot of Greek letters there, so it looks a little different than we usually see it, but it's, the probability of a success to the number of successes, the probability of a failure times the number of failures, and there's a thing that counts up the number of ways you can get successes and failures. And then this thing called the beta distribution, and I'm picking the beta distribution for the same reason I picked the gamma distribution, is if you just look at these things, they look a lot alike. This is a probability distribution at H. H is random, the number of hard counts, pi, the proportion of hard counts is a parameter, it's fixed here. Here, the pi is the random variable. It's the, I'm going to put a beta prior distribution on the probability of a hard count. But if you look at these two things, you can see that when I multiply this one by this one, there's going to be a lot of simplification. Okay. We sometimes call these things hyperparameters, the same as the gamma distribution, the alpha and the beta. I can pick them. We don't expect to estimate them from the data, but they're parameters that I can adjust that control my prior. Again, the beta is a flexible class. I think I have just a bunch of pictures of it. You can see you can make beta distributions look like caves. You can make them look more like actually Gaussian distributions. There's these U distributions. There's skewed distributions. If you're going to stick in this a flat one too, it's not on there, uniform. But if you're going to stick with on the unit interval, there's just about anything you can imagine you can write down with a beta distribution. And like I was kind of alluding before, I won't go through the math, but it's also conjugate. So if you beta prior, binomial likelihood, the posterior is also beta. And you can also see there's this kind of summing going on. So maybe if I write down, I think on the next slide, I write down the mean of this distribution, which probably makes it a lot more obvious. Yeah. This is the posterior distribution of the proportion of hard counts. And again, if you were just looking at the data, what would you do? Well, you would take the number of hard counts divided by the number of counts, just that part. And what the Bayesian distribution does is it adds alpha, that hyperparameter, to the number of hard counts, and alpha plus beta to the total number of counts. So the prior has as much information as an additional alpha plus beta counts, of which alpha are hard counts. So again, you can look at, if you're looking at a previous data set, you can quantify clearly what prior distribution you want based on a previous data set. Let's see, what does that say? So the posterior is an average of the data and the prior, and essentially based on like an argument based on what I just said. We can interpret alpha and beta as prior hard and soft counts. As n increases, the choice of prior matters less. You can see if I fix alpha and beta, as I get more and more data, the alpha and the beta become irrelevant. So that's kind of nice. Okay, so this is R. R is a software package that statisticians love, but it's pretty easy to like just read and turn it into something else. Especially at the level we're going to be doing here, just doing some illustrations. So what I've done there, as you can see, I have, again, a small data set that has one hard count, 3 soft counts. I use a relatively non-informative prior because alpha and beta are both small. It's 2, they sum to 2. So they have half as much information in the prior as the data set. So even though they're relatively small, it's still, because the data set's very small, it's still maybe a bit of information. But again, I'm just trying to illustrate. And then I'm going to get a Monte Carlo sample. And because I know the posterior distribution, is here, the parameters of the posterior are going to be beta, hard plus alpha, soft plus beta. So that's all that is doing there. I'm collecting a sample R, a random sample from a beta distribution, the sample size and the parameters. And then I can estimate, since I have a Monte Carlo sample, I can estimate the mean just by averaging them, the standard deviation by taking the standard deviation. And here I'm going to compute a 95% interval I'm sorting the values. I'm going to take off the 5% of the smallest and the 5% of the largest, and 2.5% and 2.5%, and end up with a 95% interval. And this is the result. So again, but from Monte Carlo, everything works very easy. This is just one observation. If I do the kind of the regular thing, and I get an interval by taking my estimate and go plus or minus 2 times my error bars, I get something that becomes negative. And again, this is a probability, so it can't be negative. This is equal tail, so that's completely fine. And what's going on whenever you do plus or minus 2 standard errors, or plus or minus any standard errors, you're assuming your distribution is Gaussian. Gaussian is where that makes sense. That's where the plus or minus 2 comes from. It's probabilities based on Gaussians. So if you look at a distribution, this one doesn't look too bad, but if it's not Gaussian, don't do this. Or if you do this and you're a value outside your parameter space, realize that the problem is you're doing something, you're making Gaussian assumptions that are not warranted. So if you go back to the more basic things, you'll be fine. Okay, this thing's going the opposite direction of what I expect. Okay, so hardness ratios again. Well, another hardness ratios, we can illustrate another thing, which is transformations of parameters and how they affect things. So we started with the hardness ratio that said that we're interested in the relative expected counts, hard counts versus total counts. But sometimes this is quantified and said by the simple ratio, 1 minus pi over pi, or lambda over just the ratio instead of plus soft over hard. A color, which takes the logarithm of pi, or the logarithm of the simple ratio actually, and this thing called the fractional difference. All of these things are different ways to summarize the hardness ratio. And it's not uncommon that you might be interested in different parameterizations. So it's a simple way we can look at the effect of parameterizations in a Bayesian context. So what I've done here is I have just, another nice thing about Monte Carlo is any kind of transformation, once I have a Monte Carlo sample, I just transform that sample. I don't have to do any new mathematics. So 2 slides back, I got a sample from pi, by using that R beta function. And to get this sample, the simple ratio, I just go 1 minus this divided by this. I'm just using exactly the functional form of this other parameterization. I'm just applying, I have a sample of this, and so I'm just applying this transformation to pi to get the posterior distribution of the sample ratio. And the same for color and fractional difference. So you can see the 3 different posterior distributions, and they look very different. In particular, if you wanted to compute equal tail intervals or HBD intervals or plus or minus 2 error bar intervals, you would get very different things for these different. They would compare differently. So the HPD interval here is going to be kind of in the middle. HPD interval here is going to go all the way to the minimum value because it's very skewed. This distribution looks kind of Gaussian, right? And this one it turns out that pi and the fractional difference is a linear transformation. So the distribution looks exactly the same. It just goes from -1 to 1 instead of 0 to 1. So one thing that's really nice about the color in this situation is I don't have to worry about HPD versus equal tail versus plus or minus 2 standard deviations, because the distribution looks Gaussian. So from a statistical perspective, if I can do a transformation which makes the distributions look Gaussian, a lot of things become much easier. And it also tends to be a natural parameterization to work on. And you can say, I can estimate the color. I can say the color and the estimated color and its error bars. And I've told you pretty much everything. So, we're back to the simple situation. So if you can ever kind of do a little transformation of things, make things look Gaussian, you'll make your life easier. And it turns out that often the Monte Carlo samplers, everything works a little easier if things look Gaussian. This is in 1 dimension. You typically have multiple parameters, so you can transform the different versions, the different parameters separately, and hopefully get them all to be Gaussian and have nice linear relationships. Everything becomes nicer. We won't worry about. Okay, so what's next? Oh, okay, interpreting. So more on prior distributions. We're trying to get back to what Vinay was asking about eventually. So interpreting prior distributions and different kinds of prior distributions. So
using hardness ratios for illustration. You can think of a prior distribution. The nicest way, and whenever I'm faced with somebody who doesn't like Bayesian ideas or Bayesian thinking, what I talk about is the first one, population or frequency interpretation. So maybe I have to have a prior on a mass for a star. I know the distribution of masses of the stars in the Milky Way galaxy. This is a star in the Milky Way galaxy. Why don't I just use that population? It's maybe not exactly perfect, but I have a population distribution, and I can use that as the prior for my particular situation. It's pretty hard to argue with that sort of an analysis, right? It's a star in the galaxy. Stars in the galaxy tend to look like this. I'm going to use that. State of knowledge, a subjective probability distribution. That's something about what I believe about this particular source. Maybe it's based on, research on the literature or previous observation of the source, or maybe it's a little bit my gut instinct. That's going to be a little bit less convincing, but maybe there's some of that in some cases. Or maybe you're in a situation you don't know what you're looking at, right? You don't want to say anything at all, that more than you absolutely have to. So you might have a prior that tries to quantify a lack of knowledge. A uniform distribution corresponds with no prior information. We'll see if we believe that or not, but that's one way you might think of it. The choice of prior distribution, this choice of prior distribution, because a uniform 0, 1 is a distribution with a mean, right? Its mean is a half. And so if you're averaging the data with a prior with mean a half, well, yeah, it's actually going to pull the posterior distribution towards a half. Maybe not very much, but it does have some impact on your analysis. And so we'll think about that as well. I'll refer to subjective and objective Bayesian method. So this is clearly subjective. This one is trying to be objective, and this one is trying to be objective as well. So let's look at I don't want to talk too much about this. There's a whole literature on people working on trying to come up with what are called reference prior distributions or objective priors. They are specific to the particular problem. So a reference prior is a prior that can be used as a matter of course under a given likelihood. That is, once the likelihood is specified, once you decide it's a Poisson model or beta binomial model, whatever it is, the reference prior can be automatically applied. So these tend to be derived in more standard models, and often in astronomy, when you get to it, there's a lot of complication. So it's going to be hard to look up a reference prior, but you might be able to still use the idea of a reference prior to set your own prior. So a reference prior might be formulated in order to do something that seems quite objective. It's not about your data, but maybe you're trying to minimize the information conveyed by the prior or optimize other statistical properties. So you might have, this is the posterior variance. You might try to pick the prior distribution that maximizes the posterior variance for any data set. So of all possible priors, probably in a family, maybe using a beta distribution, so within a family, but a flexible family. Of all possible priors, this is the one that brings the least information. That's a criterion, a mathematical criterion that you could try to derive. Maybe you would do it numerically in a complicated model. You wouldn't maybe get absolute optimization, but you'd be using a prior that you could argue is really not very influential. These are often formulated in terms of entropy. Non-informative prior distribution is a prior that aims to play a minimal role in the statistical information. Often people use flat or uniform priors. So there's a problem with flat and uniform priors that you need to be aware of before you use them. And so I'm going to go back to my hardness ratio example. So I have H, again, follows a binomial distribution. That's the number of hard counts. Now I'm going to put a uniform prior on pi, the probability of getting a hard count. But I want to think about what is that prior, if I put a uniform prior on pi, what does that mean for the simple ratio or the color or the fractional difference? So
So I'm doing exactly what I did before, but it's even somehow simpler. I sample from a uniform distribution. I sampled kind of quite a lot, 100,000 values from a uniform distribution, R uniform 0, 1. That's my prior on the pi, the hardness ratio. And I just want to see what that prior corresponds to for these other things. So I just compute the ratio, the color, and the difference, using again the standard, or the transformations. And the last bit is making the histograms, which are here. So you can see that if I decide I want a uniform distribution, say on the hardness ratio pi, but I'm actually interested in the simple ratio, I haven't specified the uniform prior on this thing. Why not put the uniform prior on this thing instead? Or on this thing? Right? The fact of the matter is that uniform is not, the idea of being uniform is not, it doesn't transfer from one parameterization to another. So by just saying you're uniform isn't quite enough. Then you have to think about what is the natural parameterization to be uniform of. And that's a whole nother, it's maybe just as complicated as deciding what the prior you wanted in the first place. Honestly, if I saw, well, it's actually not the prior so much. But this is these are the posterior distributions. If I saw posterior distributions looking like this, and I had to say, where am I going to put a uniform prior? Where does uniform mean really uniform? What is it? When uniform is what you think of as uniform, I would say, do it here. Hard to justify that in a mathematical way, but in its experience and instinct, this is where this bell curves, when they get wider and wider, they turn into something flat. What does it mean for this thing to get wider and wider? I'm not even sure what question I'm trying to ask, right? Here, uniform seems kind of more meaningful. So again, try to work in parameters that tend to make things look like Gaussian distributions if you can. Okay, so that's what I say at the bottom here. Why not use a flat prior on the color? I guess I use size, the color here. Well, there's a problem with using a flat prior, a complication, I should say, with using that flat prior. And that is the flat prior, the color can take on any real value. It can go to minus 100, plus 10,000, any value is possible in principle. So if I put a uniform prior, on the whole real line, well, that's not a distribution. I can't integrate it, right? I can't integrate over the whole real line. And get a constant, it becomes infinity. It's not a real distribution. It's not a probability function. But maybe we can just ignore that and see what happens. Well, that's what's called using an improper prior distribution. An improper prior distribution is a positive valued function that is not integrable. That is, I can't, I'm supposed to be able to integrate over all the possible values and get one. It's not possible, but is used formally as a prior distribution nonetheless, but by being a bit more careful. There's extra things you have to check. Because improper priors are not distributions, we cannot rely on the probability theory alone. The big fear of using an improper prior is that if the posterior distribution is also improper, then all the calculations you do are meaningless. Right, sampling from it, and none of it really makes any sense anymore. And the real issue is if you have a complicated parameter space, you have tens or hundreds of parameters, and you're using improper priors, you could find that you don't really know if you have a posterior distribution, a real posterior distribution or not. And so things can kind of, the rug can get pulled out from under you. So you have to be a little careful when you use these things. However, improper prior generally cause no problem so long as we verify the resulting posterior distribution is a proper distribution. That's mathematics, so you have to do something extra. If the posterior distribution is not proper, no sensible conclusion can be drawn. So, I mean, you'll have your, what do you have to do in that second bullet? You have your likelihood function, you have your prior, that's the posterior. You have to look at that thing and convince yourself using techniques from integration that the integral is finite. So, it's a little tricky. I don't know why I can't keep track of which way these slides are going. Improper. Okay, so let's go back. Let's use it. Let's see what the improper prior looks like. Vinay was asking kind of about the Poisson, but I kind of worked it out in the binomial one. It turns out that this thing, if you use a flat distribution on the real line for the color, if you transform back to the probability, you get a beta 0, 0. So that sounds like a good prior, right? The prior is bringing you as much information as no data, of which none of them were hard. That sounds pretty uninformative, right? But we just have to check to make sure we get things that are the posterior that's proper. And what that means in this case, it's easy to check. I need this to be a positive number, and I need this to be a positive number, which means I can use this prior so long as I have at least one hard count. It's actually a bit more tricky than what I just said. But yeah, this n minus h, that's exactly right. You have to have at least one hard count, and you have to have at least one soft count. Again, a pretty low bar, but if you're, you remember if you had a lot of data, you probably wouldn't be just computing hardness ratios. You'd be doing a proper spectral analysis, computing a power law and fitting the lines and everything else. So it's a method. It's an idea, it's an objective that you want to estimate the hardness ratio when you do for very small data sets. And if you're doing it for a population of sources, you probably will find some cases where you have very, very little data. But in this particular case, still, it's a pretty low threshold. But that's the kind of thing you need to check. Improper. Oh, yeah, okay. So just coming back to the kind of these reference priors, the objective base. This is the posterior variance. It's a bit of a formula, but if you look up, you can just look up the beta distribution and say what's its variance. This is the variance of the beta distribution, and that reference prior idea. You have an objective criterion, like I was saying before, like maybe I want to maximize the variance for any given data set. So I'm going to pick alpha and beta to make this thing as big as possible. Well, because there's alphas to powers in the denominator. The way that I do that is make alpha and beta as small as possible. And in fact, in the limit, taking them to be 0 is the kind of an objective choice. So this is, again, just in the simple example, the kind of, how would you derive a reference prior?
Why maximize? You
Oh.
want the variance to be smallest.
Yeah, but okay, so okay, right. So ultimately, you want a small variance. But remember, the knob I'm turning is my prior. The data I'm saying, I fix the data. I have h hard counts, n minus h soft counts. I'm going to pick my prior. I want my prior to bring as little information as possible. So make the variance as big as possible of all possible priors. With the data, of course, I want the data to reduce the variance, right? I'll talk about Jeffrey's invariance principle. It's a little bit of a funny principle. It comes up a lot. So Jeffrey's, he's a famous statistician, and he really didn't like this. My criterion was uniform. I said I wanted a uniform prior. That's what I mean by being non-informative. But it depends on whether or not I use the log transformation or not. He didn't like that. He wanted an idea of a non-informative prior or a reference objective prior that doesn't depend on the transformation you pick. So he derived something that you don't have to worry about the transformation. So Jeffrey's invariance principle says that any rule for determining a non-informative prior should yield the same result if applied to a transformation. If I take the log, anything else, it should not matter. Note, any subjective prior should adhere to this. So if I tell you my prior beliefs about the color, and you ask me about my prior beliefs for the probability of a hard count, if I am coherent, I should give you something that's consistent. pretty hard to actually do in practice, but in principle, subjective priors should automatically have this effect, but maybe not these non-informative priors. So I don't want to go into too much detail, but what Jeffries came up with, just show you how you derive them. He came up with this thing, which is based on the expected Fisher information. So this thing, the log,
This is the sampling distribution. The log, so it's the likelihood essentially, the log likelihood, and he's taking the second derivative of the likelihood. That's the curvature, right? And so that's why it's called the Fisher or the information matrix, is because as this quantity gets bigger, I have more and more information as the curve, the likelihood becomes, steeper and steeper. So it's something, this quantity comes up all the time in frequency analysis when you're trying to estimate uncertainties based on likelihood function. Jeffrey's going to use something different, but it's a standard quantity. And he did a little bit of mathematics and noted that if I make my prior distribution proportional to the square root of that thing, I get a prior that meets his criteria. If you're not, this is one dimension because these, the densities are a one-dimensional thing, so you have to put a determinant on there. If it's this becomes partial derivatives, but think about one dimension. It's easy enough. So what does that look like in say our binomial model again? So the first thing I'm doing there is I'm computing at the top the log likelihood. So we have the probability of a hard count to the power number of hard counts, the probability of a soft count to the number of soft counts, taking the logarithm of that thing. Take the derivative twice, the derivative of log pi is du over u, and then you have 1 over pi, and take the derivative again, you get a pi squared and a minus sign in the denominator. So it's this thing. I take the expected value because h is the number of hard counts, and it follows a binomial distribution. The expectation of h is pi. Going to cancel with one of these. The expectation of n minus pi is n times 1 minus pi. And so, it's relatively straightforward kind of calculation. You get this thing. And so his prior is going to be proportional to the square root of that. And that turns out to be a beta 1/2, 1/2. So it's a little bit funny, but if I use this criteria and this prior, which is also it is a non-informative prior, right? It's like I have one count. Couldn't really happen in practice, but the information is the same as one count, half of which was hard and half of which was soft. That's okay. It does seem relatively non-informative in this case. And so I say at the bottom, I say, this prior is invariant, but is it non-informative? In this case, it is. And it turns out in practice, it tends to be. But to me, it's always a little bit funny because we use it for non-informative, but the definition is all about this invariance, which is a nice property, but it's not really clearly related with non-informativeness. But you'll hear people talk about Jeffrey's priors. And if your model's not too complicated, it is something you can do. And it is kind of quite objective because it's not based on your data or your beliefs. It's based on an algorithm to get some nice properties. So it's something to consider. At least it does get kind of complicated again if you have a complicated model, but it's kind of a nice thing to have in your back pocket. And maybe I'll finish with this. Yeah. One more thing to think about with uniform prior distributions. Uniform prior distributions, astronomers, in my experience, especially cosmologists, I think cosmologists in the room, really like uniform priors. They really like them. And they're, you want to keep them as a possibility, but you want to be aware that when you're using a uniform prior, you haven't already become, you have made decisions and choices that may have an effect on your analysis. Like I said before, the scale that you pick determines which if you take the logarithm of your parameter, it's no longer uniform. Another thing to be aware of with uniform priors is this, that first question. Suppose pi is uniform 0, 1. What is the probability that pi is in the interval? Is it easy to put this thing back up? It's otherwise people do it too.
So I have 0 and 1. And I have a uniform prior, and what I'm asking is I have some epsilon value, which epsilon, this means some small value. And here's 1 minus epsilon. What's the probability that I'm between epsilon and 1 minus epsilon? Well, there's going to be epsilon area here, and there's going to be epsilon area here. So it's 1 minus 2 epsilon. So the most of the probability is going to be in that interval that's, just cutting off a tiny bit off each corner. Now suppose I don't have 1. This is part of what's called the curse of dimensionality. Now suppose I don't have 1 parameter, but I have capital K parameters. And I put
Uniform prior on all of them. It's equally non-informative, right? What is the probability that all of those parameters are in that interval? Well, they're independent. And so the probabilities multiply. So what I get is that same thing, 1 minus 2 to the epsilon. But since there's K of them, there's a K in the power there. And the funny thing is that as K gets bigger, as I get more and more parameters, this goes to 0. So where is all the probability? The probability has to sum to 1, but the probability in the box, a high dimensional box in the middle that goes almost all the way to the edge has 0 probability. Where's all the probability? It's all around the edge. And the problem is in dimensions is, it's hard to comprehend this, right? But as you get into higher and higher dimensions, volumes do funny things, right? So the volume of a hypercube in high dimensions, almost all the area is along the edge. So so if you have 100 parameters, what you're doing is you're saying by putting a uniform prior, you're also accidentally are saying you think the likely values of the parameters are very close to one of those edges or multiple edges, which is probably not what you meant. Right? So uniform, that's just a word of warning. There's not anything to do about that except don't use uniform priors and think that you're off the hook of having to think about priors, essentially. So I think I'll stop there since it's almost 12.